take out lecture 25 from Wednesday's class, we're going to work on the last two problems we didn't get to finish up on Wednesday. Actually, today's lecture and Wednesday's lecture is just one big section. So Wednesday, if you notice, there was just a lot of like talking and not a lot of time to work in groups. Today, we'll probably spend 20 minutes, maybe 25 minutes, and the whole rest of the period, you're going to get a chance to practice graphing these polynomial functions. So project number 4 I handed out, and if you turn project number 4 over, notice that the very number 1 of project number 4 says construct your GCC student ID number polynomial due April 9th. That's next Wednesday. And that's because if you turn on the front page, it shows you how to construct your polynomial with your student ID right at the top. Now, the reason I'm asking for you to pass that in is because in the past, I've waited to collect the projects. And if you get number 1 wrong, the whole thing is wrong. So I just figured it's probably better and it can really be, you know, just put it on a slip of paper with your name on it. So just put your student ID on a piece of paper, construct this polynomial, and just let me check it before you go on and do all this other work. Now, you can hand that in to me Monday if you want, like if you want to get going. But I just hated, you know, the fact that there would always be 1 or 2 students in each class that would just do that first part wrong, and then everything else was just kind of whatever. So anytime between now and Wednesday, even if you get here early and you just want me to check it, and I just put a check on your paper, that's fine. I just don't want you doing, you know, 2 through 13 and then finding out it's all, you know, not working, okay? So that's just a little check for you. The next 2 weeks, it's actually now the next week, I have a sign-up sheet on my office door for advising week. You're welcome as a student to put your name in there, even if you're not my advisee, for 1 or 2 slots. Each slot is a half an hour. If you want to come in and go over anything from this exam when I hand it back to you today, anything that you're not feeling comfortable with in the class, if any of the new material, whatever it is. So we have 1/3 of the semester left. So you can use that time. I know some of you said you can't make my office hours, but I'm always available other times during the week. So feel free to sign up if you want to come in. Okay, so let's see. This is where we left off, number 11 with class 25. And it says find the zeros. Now remember, when you see zeros in your mind, what are you going to think of? What do you think of when you find the zeros of a function? What do you think of? Do you have an image? Do you have a word? What do you think of? X-intercepts, right. And what do you know about x-intercepts? Your output, f of x, is equal to 0. Okay, so we want to find the zeros of this function. The good news is that this function is already factored for you. I wouldn't want to multiply all those factors out and try to factor it. That would be awful. Give the multiplicity of each 0. That was what we talked about on Wednesday. State whether the graph crosses the x-axis or touches the x-axis and turns around at each 0. So let's find the zeros of this function f by setting this whole thing equal to 0. So let's do that. And you notice that the little constant out in front, the 1/9, doesn't affect the zeros at all because it's a constant. In our polynomial, when we wrote our polynomial like this the other day on the board, and we were looking at how we define a polynomial, and we kept going ... down to a1x plus a sub 0. What does this 1/9 correspond to in this polynomial form, not in the factored form? What does the 1/9 correspond to in this model, this representation? Where would you find the 1/9 if I multiplied this all out, all those factors out? Where would that 1/9 appear? Excuse me? A. Well, there's lots of A's here. Which one? Do you know which one it would be? A sub n, right, because it's the leading coefficient. It's in the front of the pack, right? The 1/9 is in the front of this whole thing, and it would be the leader right here too. So that 1/9 is A sub n. It's the same thing as the coefficient of, it's your leading coefficient. And it never changes whether you have your polynomial in factored form or whether you have it in your adding and subtracting or your polynomial form. It never changes. It's always the same value. So now we have to figure out, before we find the zeros, what degree is this polynomial? Well, you say, geez, I just look for the highest exponent, right, when it's in polynomial form. What do you do right now? Because this is not polynomial form. It's all multiplication. It's in factored form. So how are we going to find out what the degree of the polynomial is? Anybody have an idea? A guess? Could this be a linear function? No. Everybody says no. Why are you saying that? Let's take this out. I want to put it on a new page. That's not going to be a very good picture. No, let's try it again. Cut. Well, that will be a little better, but not much. All right, good enough for us to get to what we want to do. Cut, paste. All right, so here's our polynomial. The degree, so if this was written like this, 1/9 times x, and whatever that power is there, there's going to be a bunch of these terms, right? Bunch of them. I don't know how many. If I wrote it in polynomial form, I'd be looking for the highest power. So how would I figure out what that power is from looking at this right here? What if I asked you to multiply this all out? How would you start? How would you start to multiply it all out? What would be the first thing you'd do? Forget the 1/9 for now, because that's here. How would you multiply this out? So I'm asking you to multiply this out. I'm not asking you to do it right now. I'm just asking you, how would you start to multiply that? What would you do? Okay, x plus 3 times x plus 3 first. You do that first. Then what would be the highest degree when you multiply this out? What would be the highest power? X squared, right? And I don't care about the rest of the junk, because I'm just looking for the highest power. So from this, I'd get an x squared plus a lot of junk, right? Then I would multiply it by x plus 1. That whole thing. But what would be the highest power when I multiply x squared times x? X cubed. So I've taken care of these first two multiplications. And it'd be x cubed plus and minus a bunch of stuff. And all that, blah, 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 would be multiplied by x minus 1 quantity squared. So I got an x cubed out of here. What's the highest power that's going to come out of x minus 1 quantity square? If I multiply that out. An x squared. So I'd have x cubed plus a lot of stuff times x squared plus a lot of stuff. So when I multiply these two, what's the highest power I get? X to the 5th, and I got a bunch of stuff after that. And then I multiply all that by, what's my final thing? Oh, thank God, x minus 3. So when I multiply x to the 5th times x, what am I going to get? X to the 6th, right. So this is, thank God I didn't ask you to multiply it out. You'd be here the whole rest of the class. So this would be a 6th degree polynomial. So how are you going to figure that out? How can you figure out from looking at the factored form that your polynomial form would be degree 6? What could you do?
Square terms each have 2.
All right, so these each have 2, so you add those together. 2 plus 2, what do you get? 4. And what about those other factors there? What are they going to have for a power? 1. So when it's in factored form, to find the degree in factored form, you add up all your exponents. So to find the degree in factored form, it's 2 plus 1 plus 2 plus 1, which is 6. So that means if you multiply that monster out, the very first term would be 1/9 x to the 6th. Because that 1/9 is your leading coefficient, that never changes. And to know the power for x, you simply add those exponents. Okay? Now, let's go back to our graph. So, this polynomial is going to be x to the 6th. 1/9 x to the 6th plus a bunch of junk. Is that an even or an odd degree? Even. So what do we know about the end behavior? Because it's an even degree polynomial. What do we know about the arms of the graph as the end behavior as we go out to the left and right? What do we know about the arms? They're the same. They're either up or they're down. What's the leading coefficient? 1/9. Is that positive or negative? Positive. So since a sub 6, I call it a sub 6, that's the leading coefficient. And the reason I put the 6 there is because our highest degree is 6. So our leading coefficient is equal to 1/9, and that's positive. And I have an even degree. So I know whenever I graph this function, my arms and my end behavior are going to be pointing towards the heavens like that. So that's what I know right now before I even start to try to graph this thing, that this graph is going to rise as I move to the left and the right towards positive and negative infinity. So before I do any work, I know that much. Okay. Now, let's find the zeros. If we set this polynomial form equal to 0, the 1/9 doesn't come into play because 1/9 will never equal 0. So all I have to do is look at each factor and figure out when each factor is going to equal 0. So what value of x will make that first factor equal to 0? X plus 3 equals 0. What will make that 0? -3. So 1 0 is going to be -3. How about the 0 for that one? Cassandra? -1. 0 for that one, Paul? Yeah, and he answered for the last one, 3. Okay, so those are each of our zeros. Notice it's in the form x equals a number. So we can right away now go on to our graph and put a little solid dot on the x-axis at -3, -1, 1, and 3. So -3, -1, 1, and 3. Those are my x-intercepts, so I can put dots right there. All right, so I can do that. Now, I need to know what happens at those x-intercepts. Does my graph come down and touch it and go back up? Or does it go through? Does it flatten out and go through? What does it do? That's what your multiplicity tells you. So let's look at the multiplicity of each of these zeros. X equals -3 we want to look at that exponent. That looks like a parabola, so that has multiplicity 2. That tells me I'm just going to touch the x-axis and turn around at the point -3, 0. At that x-intercept, I'm going to come down, touch it, and then head right back up. It's a turning point. Let's look at the multiplicity for the 0, -1. The multiplicity for the 0, -1, you can't see it, it's not there, but we know a 1 is there. That's odd. So you think of your linear function, your straight line, that crosses right through your x-axis. It has multiplicity 1, so you cross through x-axis. It's just like a line. A line would cross right through your x-intercept. And then at the 0 of 1, you have an even multiplicity again. It's 2. It's going to be the same thing. You're going to touch the x-axis and turn around. And then your final 0 at x equals 3, You're going to be odd again. You're at 1. You're just going to cross and go right through. So we can now visualize this function. We can get a sketch. It may not be totally accurate, like where you put your like relative maxes and mins may not be accurate, but you can get a graph here of this quick sketch. Okay, so let's see. How are we going to start this? Well, our end behavior tells us we're way up here, and we're going to come down. And when we hit this -3, our multiplicity is 2, so I'm just going to swoop down and then come back up. But notice, at -1, I've got to come back through because it's an odd multiplicity. So I'm just going to do something like this. I'm going to come down. I know I turn around at -3. I don't know how high up I go. Maybe I go that high, and then I got to come back down at -1. We have a factor of an exponent of 1, so I have to cut through. Now I don't know where my y-intercept is, so that's the one other point I've got to find. So let's find our y-intercept. What's the y-intercept? It's when x is 0. So we go into our function and then we put a 0 in every single spot where we see an x. And we solve that to find our y-intercept. So let's do that. What's f of 0 going to equal? 1/9. 0 plus 3 is 3. 3 squared. 0 plus 1 is 1. 0 minus 1 is -1, but when I square it, I get 1. And 0 minus 3 is -3. So let's see what this comes out to be. 1/9 times 9 times 1 times 1 times -3, which is 1 times 1 times 1 times 1 times -3, which is -3. So 0, -3 is my y-intercept. So now I know where to head, where this graph is heading towards once it crosses over here at -1. I come down here at my y-intercept. I'm going to cross over, and then I head back up to 1. What happens at 1? I've got to come back here and look. At 1, I have a multiplicity of 2. So I can't cross over. Multiplicity of 2 means I'm going to look like a parabola. So I come up here, I turn around, and then I head back down again. I don't know how far down I'm going to go, but at some point I got to head back up, cross over, and put my arms up. So that's a fairly accurate sketch. Again, this could be much higher, this could be much lower. You're not going for accuracy, you're just trying to get a sketch. Let's take a look at what this thing really looks like to see how close I got here. So let's see. So I want to read me I know it's 1/9, 1 divided by 9. And then what do I have? I better put that in parentheses. Hang on, just to. Let me put that 1 divided by 9. All right, so we have x. Is it x plus 3? X plus. Oh, do I even have to like have someone tell me what the equation is? I can look at this. Because if -3 is a 0, I know what my factor looks like. X take away -3 or x plus 3. So I look at this. I know it's x plus 3 because it's been moved to the left 3 units. And it looks like a parabola. So I put a square on it. My next one, if I blew that up right around -1, it would look just like a straight line. So that's going to be x plus 1 raised to the first power. And if I look at this, it's 1. It's been shifted to the right one, so it's x minus 1 if we use our transformation. X minus 1, and it's a little baby parabola right there, so I square it. And then my final one, straight through. So that's x minus 3. All right, so let me just do zoom 6 and see what this thing looks like. Okay, so you can see the only part I wasn't very accurate with is that this dips down really low, much further than what I have here. Okay, and we could find that point by changing our window or looking for a minimum value. Okay, because on this graph, this point way down here, so let's change the window a little bit. Let's make y minimum like -30 and then graph it. Okay, so if I actually wanted to find this point here, the minimum point, I would go to second calc, and I'd go down to minimum if that's what I was interested in. And I would do my left bound, that's good, my right bound. I just got to move past that point. There we go, I'm past it. Enter. There it is. It's at 2.49651, and that's the lowest, the minimum value. That's the absolute minimum. There's no other y value that's ever going to be lower than negative 13.23477. Okay, that is your minimum in this entire function. Why? Because your arms go to positive infinity. So you'll never get anything lower than that. So that's the real graph. Okay. All right, so now you have one to try. We've reached a turning point. So let's see if we can get through this. What is the degree of this function? I don't have the whole picture here. What you want to tell me the entire function here? It didn't fully copy. I have x to the third. You have it on your paper on
Minus 4x.
yeah,
4.
plus 4?
Yep.
Okay. So what's the degree of that polynomial? 3. And you just, when it's in polynomial form, it's easy for you. You just have to take the highest power. So the degree is 3. How many real zeros does this function have? How many real zeros? Just means your zeros are real numbers. How many zeros does it have? Alana told you where to look for your zeros about 10 minutes ago. Where are you going to look for your real zeros? Your x-axis. So let's see, you got one x-intercept, two x-intercepts, 3. So you have 3 real zeros. What are they? What are your real zeros? What are the values for your real zeros here? Negative 2, 1, and 2. Okay? Now, if I were to put this in factored form instead of polynomial form, if I know a 0, I know a factor. So if I want to put this in polynomial form, that 0 looks like this. That 0 looks like this, x plus 2, because I do x take away a negative 2, and it becomes x plus 2. Is it going to have 1 for a power or 2? Am I going straight through like a line, or am I turning like a parabola? It's going to have 1 because I'm going straight through. Okay. What about this point right here? Am I going straight through there? Yep. So let me give myself some space now. So we're going to write this both in factored form. So here's the polynomial in polynomial form. What's my leading coefficient here? What's a sub 3 right here? What is a sub 3? What's my leading coefficient? 1. It's not there, so put it in. There it is. Okay. So that means in my factored form, I'm going to have the same leading coefficient. I'm going to put the 1 out there. So my first factor looks like this. 2, negative 2 is a 0, so x take away negative 2 becomes x plus 2. My degree is 1 because I go straight through. My next x-intercept is 1, so x take away 1, my degree is 1. My last x-intercept is 2, my 0 is 2, so x minus 2 to the first. So in this form, to get the degree, you have to add these 3 things. 1 plus 1 plus 1 equals 3. So they agree, so you did it okay. So this is what this particular function looks like in factored form. This is what it looks like in polynomial form. How many turning points does it have? How many turning points does it have? Tyler? What are they? Right, so the 2 turning points, the coordinates are negative 1, 6. Okay, that's a relative maximum. That's coordinates for a relative maximum. And the other turning point, if we estimated it, you can probably see it on your paper. I can't see it here. What is it on your paper? The other turning point, which is right here. You have the coordinates, right? 1.5, comma. Okay. And that's the coordinates for a relative minimum. Okay. If I asked you for the relative maxima and minima, I'm just looking at the output values. So the relative maximum is 6. The relative minimum is negative 0.875. I'm just interested in the output value. The reason I can't call them absolute is this thing continues to go towards the heavens, so that's not ever going to be an absolute maximum. And on the left-hand side, the left-hand end behavior goes towards negative infinity. So we're on class 25, Ken and Chris, if you don't know where we are, the last part of class 25. Okay, so what happens at each turning point? Well, your function's increasing, increasing, increasing. You hit this turning point, and then you decrease, 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 decrease. You hit this turning point, you increase, increase, increase. So at each turning point, your function changes from being either increasing to decreasing or decreasing to increasing. That's what happens at each turning point. You only have to visualize it. You can see it in your mind if you think about what happens to your function at each of those points. So this is important right here. That's why it's in a box. In general, if f is a polynomial function of degree n, then the graph of f has at most, and that's a very, very important language, at most n minus 1 turning points, and at most n real zeros. So let's take a look at this function again. It was f of x equals x to the third minus x squared minus 4x plus 4. So if I just put this on your next quiz and said, and you didn't have your graphing calculator, and I said to you, what's the maximum number of turning points this thing can have? You would say, well, my degree is 3. So the most number of turning points I can have is this, n minus 1. So it's 3 minus 1, which is 2. This is the maximum number of turning points for any cubic. For any cubic polynomial. You would say, well, can I have no turning points? And yeah, think of your parent function. The parent function here is x cubed. That doesn't have any turning points at all. It's always increasing. So the question is, can I have 1 turning point? That's something you can think of. Is it either 2 turning points or no, or can I have 1? It's an interesting thing to think about. Now, what about the maximum number of times it can cross the x-axis? Well, with your parent function here, x cubed, you cross it once. With this function, you're crossing it 3 times. So the most number of real zeros, most number of real zeros or x-intercepts is 3, the same as the degree. Okay, so that's going to change after we do another class or two. What this is going to say is that all polynomial functions of degree n have n zeros, not at most, because then we can start to deal with complex zeros, zeros that have an imaginary number as part of it. Okay. All right, so that's the end of 25, and today we're going to do more graphing. We'll start off lecture 26 with one more graph. Again, we're just looking at quick sketches here. So, and I give you a whole series of steps to follow, so you don't have to memorize these. So here's the first graph, x to the 4th minus 6x to the 3rd plus 9x squared. So if you were developing a cheat sheet for your next test, the last test of the semester, these steps here with an example would be a great thing to put on your cheat sheet. You really only need one example, and then you really have everything you need to sketch these polynomial functions. So here's your function. So the first step is to think about what happens to the end behavior. Okay, the leading term here is x to the 4th. Here's our leading term right there. The leading coefficient is 1. And the degree of the polynomial is 4, which means it's an even polynomial. So we know that the graph has the same behavior at each end. And since the leading coefficient is positive, we know that the graph rises to the left and rises to the right. And this is the notation we used the other day. In fact, we don't really want to use that notation. We want to separate it out. So as x goes towards positive infinity, f of x approaches positive infinity. As x approaches negative infinity, a function approaches infinity. Our arms are both up in the air. That's all it tells us. So down here, I can go right down and I can do this kind of thing. They may not be in the right spot, but I know both of my arms are going to be up when I sketch this. Okay. The next thing we want to do is to find the zeros, the real zeros of our function. To do that, we set f of x equal to 0 because they're the same as your x-intercepts. And in order to find the zeros, we have to factor. And the first form of factoring that's going to be critical for most of these polynomials is the greatest common factor. So my greatest common factor here is x squared. I'm going to pull that out as my first form of factoring. Then to completely factor it, I have to make sure each factor is factored into its prime factors, which this is not. X squared is fine. I can't factor that anymore, but I can factor this into x minus 3 times x minus 3. X squared minus 6x plus 9 is x minus 3 times x minus 3. So I've done my first 3 steps. Express the factorization in a more compact way using exponents. And what that means is, since I have x minus 3 times x minus 3, I want to write it as x minus 3 quantity square. That's so I can see what's happening at each zero. Am I turning around or am I going straight through? Set each factor equal to 0 to find your real zeros. Well, x squared equals 0 when x is 0, and x minus 3 equals 0 when x is 3. So my real zeros for this function are 0 and 3. My x-intercepts, notice how my notation's different. My x-intercepts, I actually put coordinates in. My zeros, I can either just list them or say x equals 0, comma, or 3, semicolon, whatever you want to do. Okay. Find the y-intercept. We have to know where we cross the y-axis. That's when x is 0. So put 0 into the function. And we get a 0. So 0, 0 is acting, the origin is acting as both the x-intercept and the y-intercept. It's playing a dual role. Okay. Okay, so now we want to see, is our y-axis here acting as an axis of symmetry? Do we have even symmetry here, odd symmetry, or neither? So let's review that. Even symmetry was when you plugged in opposite values of x and you got the same y value. Just think back to your original parabola. Negative 2 squared is 4 and its opposite 2 squared is 4. It's even. So let's see if this parabola is an even function. So to do that, I want to see if f of negative x equals f of x. So let's replace f of x with what it equals. Here's f of x right there. X to the 4th minus 6x cubed plus 9x squared. Now on the left-hand side, I replace x with its opposite. Negative x to the 4th minus 6 times negative x to the 3rd plus 9 times negative x squared. So this gives me x to the 4th, because negative 1 to the 4th is 1, x to the 4th is x to the 4th. However, this gives me a negative 1x cubed, which changes that 6 to positive. So already I know this isn't even. No way, Jose. All right, so it's not even. Is it odd? To check if it's odd, f of negative x has to be the opposite of f of x. Well, let's finish f of negative x here, because we got to use that for both. So here's f of negative x. X to the 4th plus 6x cubed plus 9x squared. We said that does not equal f of x. So the question now is, does this thing equal the opposite of f of x? Well, if I change all the signs on f of x, I'm not going to get x to the fourth and 9x squared there. So it's neither even or odd. It's neither even symmetry or odd. It's neither. So we shouldn't expect this thing to have symmetry about the y-axis or about the origin. So I think we're ready to go. What are our zeros? 0 and 3. Here's 0. Here's 3. Where's my y-intercept? Same place. So what am I doing at each of these zeros? What's my multiplicity? At both zeros, I have a multiplicity of 2, which means I'm going to look like a parabola. So I don't know how far over to start. I'm just going to start here. I'm going to come down, and at 0, I turn around. Boop, I turn around. So I know I got to come up here and then come back down to turn around at this point. Because my function goes from decreasing to increasing and increasing to decreasing at these turning points. Again, I don't know how far up I come. I'm going to try to make it look like this. So actually, it looks like a W. That's what it looks like. See, you don't have even symmetry here because this doesn't reflect around the y-axis. Again, I don't know whether this peak right here should be there or if it should be further up or further down. That's not what's important to the sketch. Okay, so I'm going to put in my important points here, and that's all you need. All right. So try the next one at your seats and put your flags up. If you have any questions, I'm going to come around and help out and take a look. And then you can proceed on. It's the rest of the 35 minutes is all you're working on these problems with your group or by yourself. I'll do number 3 for you once everybody gets this one done, and then you can move on to your activity in-house.